So a good day to everyone watching this video. Myself SI Vaibhav, and I am going to present to you electric hygrometer. So in this presentation, we are going to look into what are electrical hygrometers. We will look into its working principle, construction. We will look into its advantages and limitations. We will look into the theory and calibration, and we will also look into the case study. So an hygrometer is basically a device which measures relative humidity in the atmosphere. And an electrical hygrometer uses electrical properties such as resistance or capacitance to measure this relative humidity. So why one should learn about hygrometers? So they are used to measure moisture content in the atmosphere. They are used in meteorology, agriculture and food storage. They are used in industries. They are also easily integrated in digital systems. They can also help the disaster management department by detecting cyclones, droughts, and heavy rainfalls. So this is a schematic of electric hygrometer. We have an AC source which gives the current. We have an porous glass which is covered with gold films on both sides. And we also have an AC millimeter which measures the current. So this is the basic assembled hygrometer after the construction. So here we are only going to construct one thing, that's this glass part. So first we take a soft borosilicate glass. We remodel it with into a porous glass sheet like this. We remodel it like this. Then we leach out all the alkali salts present in this porous glass. And to remove the residual salts, we put this porous glass in distilled water for 3 days. And on each day we change it twice. Then we treat it with LiCl2 solution, lithium chloride solution. Now this lithium chloride solution, why we use it is, it has higher decomposition potential than water. So that's the reason why we use lithium chloride solution, salt. And we put this porous glass in this lithium chloride solution for 3 days straight. So now we have the glass part. Then we take a gold film of 0.01 micron and evaporate on both sides. And this gold film is permeable. Now we'll look at the working principle. Basically how the hygrometer works. So we'll go back to the schematic. So here we can see the AC source. This AC source sends out current. Now when the current reaches here, gold is a good conductor of electricity, by the way. So it connects here, and here we have lithium chloride. This lithium chloride is hygroscopic, so it's gonna absorb the water in the atmosphere. When it absorbs, as water is a good conductor of electricity, it conducts, and the current passes through and goes to milliammeter, where we measure the current. So the more the humidity in air is, the more the lithium chloride absorbs water, and the more the current will be. So here the voltage is constant. According to Ohm's law, V is equal to IR. Voltage is constant. Resistance is inversely proportional to the current. So as current increases, which means when relative humidity increases, that is when the current increases, and when it increases, resistance decreases. So how do we relate resistance with relative humidity is, first we put it in a control space where we can control the percentage relative humidity. Now percentage relative humidity is, now at that temperature, the amount of water vapor in the air present divided by the maximum amount of water vapor that can be present at the temperature into 100. That's percentage relative humidity. So we put the assembled hygrometer in the space where we can control this percentage relative humidity. And at each relative humidity, it will show a different current. And with current, we can calculate the resistance. And we get a curve. From the curve, we derive the empirical equation, which is this, where R is the resistance and H is the percentage relative humidity. And this is the curve. The curve is resistance versus percentage relative humidity. And this curve one is the empirical curve. Now when we look at theoretically. Theoretically, we know that resistance is equal to length by conductivity into area. Now, length here is pore length, and conductivity is concentration of the salt into equivalent conductivity. Now, here we can get equivalent conductivity from the concentration. This is the data at 25 degrees Celsius. We can get equivalent conductivity, and at that concentration, we can also get the relative humidity. Now, when we substitute this concentration and conductivity, we also get the resistance. So now we can plot the values between resistance and relative humidity. So this curve to gives the theoretical part of the relative humidity was resistance versus relative humidity, percentage relative humidity. So there are limitations to this electrical hygrometer. So main limitations definitely is the accuracy. The accuracy is very low. Then we have the sensor lifespan is very short. It can the electromagnetic interference can cause disruption in the calibration. There is higher initial cost, and we see here we also require the AC source, which means we require a power source. So these are some of the limitations. Then we go into the application of electrical hygrometers. This is a basic study where we modify this electrical hygrometer as a sensor and use it to estimate relative stomatal aperture. So basically, measuring stomatal apertures is very hard as the size is very tiny. But using this electrical hygrometer sensor, we can easily observe the relative stomatal aperture. So basically, we have a sensor, and we also have a portable resistance meter. These both are connected, and this is how the sensor looks like, and this is the resistance meter. So the sensor basically is works same as the electric hygrometer. Whatever water vapor comes here, it absorbs and gives the resistance gives the resistance value or at that relative humidity. So we first what we do is we take two leaves. Both the leaves we are going to do measure the same way. These both leaves are orange leaves. One was from west side of the tree and one was from east side of the tree. What we do is we take this one leaf, and initially the sensor value in the resistance meter is 3. So if it's not 3, we use dryer to make it 3. Then this leaf is clamped above the resistance meter. Sorry, the sensor. So what happens is water vapor, when there is water vapor, the stomata opens. So therefore, when there is more water vapor, the stomata opens more. So when this stomata opens, the water vapor diffuses through the stomata and it goes into the sensor. Now the sensor will observe the resistance at that relative humidity, and we also look at the rate of water vapor, how the water vapor is diffusing, the rate of it, the amount how much amount is diffusing, and we correlate it to the resistance, and we with the help of this we estimate the value of relative stomatal aperture. So what we do is we take a temperature range over 9 to 35 degrees Celsius and we measure transit times. So basically transit time is the amount of time. It is the amount of time that measures at that how much time it takes to absorb a certain amount of water vapor. That's the transit time. So this is basically the relative stomatal aperture formula. The relative stomatal aperture V is equals to T. This is a standard transit time, and this is a measured transit time. This one we measure, and this standard transit time we get it from table 1. In this table 1, we put the sensor over a free water surface to measure the standard transit times from 9 degrees Celsius to 35 degrees Celsius. So in this table, the temperature starts from here 0, 1 to 9. At 9 degrees Celsius, it's 100 seconds. The transit time is 100 seconds. Now, if you want to look at 19 degrees Celsius, it's 10. plus 9, which is for at 19 degrees Celsius is 40. Same at 35 degrees Celsius, 30 plus 5. At 35 degrees Celsius is 10. So as the temperature is increasing, the transit time was also very low. And from table 2, at a certain relative humidity, we also have and at a certain temperature, we also have the values of how much water vapor is transferred. Like at 18 to 30% humidity, we at 4.5 degrees Celsius, 1.2 micrograms of water vapor is transferred here. So using this data, we basically calculate the stomatal aperture. So this is the relative stomatal aperture versus at the x-axis is time, and above it we at a certain temperature how the relative stomatal aperture is. This is the basic final result. So from this we were able to see how electric hygrometers were able to measure the relative stomatal apertures. So from this we conclude the presentation that in this presentation we were able to learn the basics of electric hygrometers, the uses of electric hygrometers in our daily life, the basic construction, the theory, the calibrations, the limitations, and we also looked into a case study of the how electric hygrometers help in observing the relative stomatal aperture. So these are the references from where I created this presentation. Thank you for watching this video.